Okay, good. Hello. This is Chapter 1, Motion in One Dimension. In this chapter, we're going to talk about the laws of physics in one dimension. This is module, again, module number 1, motion in one dimension. Many textbooks, many physics textbooks, call this mechanics. We typically think of maybe car mechanics or truck mechanics, but actually, originally mechanics, and still is in the physics realm, mechanics is really the science or the physics of laws of motion, whether it's one dimension, two dimensions, three dimensions, etc. In your textbook, this is chapter 1, motion in one dimension. In chapter, let's see here. In chapter 2, we will still be dealing with one dimension, but the physics of free fall. Finally, in chapter 3, we'll deal with two-dimensional vectors, and then in chapter 4 and 5, we'll be dealing with motions in 2 dimensions. In this book, we'll never actually deal with motions in 3 dimensions. However, really, motion in 3 dimensions is a very easy extension of motion in 2 dimensions. So once you know how to do the laws of motion, physics laws of motion in 2 dimensions, it's very easy to extend that to 3. Okay, chapter 1 starts on page 5. And one of the first things this chapter does is to make the distinction between a scalar quantity and a vector quantity. In order to do that, what we will do is we'll talk about actually the quantities that we're going to be talking about in this chapter. The main quantities we're going to be talking about in this chapter are distance and displacement. We'll talk about distance, d. Displacement, typically we'll say is x. We're going to talk about time. We'll give it the symbol of t. We're going to talk about velocity, symbol v, and speed. Maybe we'll use the symbol s for speed. A scalar, let's talk about the difference between a scalar and a vector. Let me first give a couple examples of a scalar. A couple examples of a scalar would be temperature, elevation, like elevation of a mountain. Speed is an example of a scalar. So this speed actually is a scalar quantity. Okay. What actually is a scalar? A scalar is a quantity, a physical quantity that we can measure that exists in space and time. So we can say that temperature, I'll abbreviate TEMP, is a function of the x dimension, the y, and the z, and also t, time. We know, suppose we have a x, y, z coordinate system, and x, y, and z coordinate system. Like we take a room and you take the 3 walls of a room, x, y, and z coordinates. We can specify the temperature at any of these coordinates, and also the temperature may vary in time. Elevation is another good example. If you have the elevation of, say, a hill, you can go, we can plot actually the elevation of a hill in the XYZ coordinates is probably not going to change with time, but we can plot the elevation, and we can measure the elevation at any spatial coordinate. Notice that there's no sense of direction with speed, or with no sense of direction with temperature or elevation. It's just a physical quantity we measure in space. Now we compare that to a vector. A vector is a quantity that has what we call a magnitude and a direction. This is really a kind of a loose definition of a vector. There's a much more rigid mathematical definition, but for our purposes, this works well. That is, it has a direction, a magnitude, and a direction. For instance, velocity. Velocity is a vector, and whenever we write a vector, I'm going to put this little arrow with this little arrow to signify that the quantity we're talking about is a vector. The velocity would be a velocity vector would be in examples like 35 miles per hour going in a certain direction, let's say east. So there's the magnitude of the vector, and that's the direction of the vector. We have to have both in order to quantify exactly what that vector is. The speed, we can say, the speed is simply the magnitude. 35 miles per hour is a speed. That's a quantity, but there's no sense of direction. We don't know which direction that 35 miles per hour is going in. Okay, so another way to write this would be, for instance, the speed is the magnitude or the absolute value of the velocity vector. I'm not even sure the textbook has that, but in more advanced physics books, we would often write it this way. Okay, time is a quantity that marches forward. We wouldn't talk about time as in a vector sense. Distance and displacement. We're going to use, what we're going to say is, we're going to say distance is a scalar quantity and displacement is a vector quantity. Okay, so and I'm looking here on in my textbook, page 8 and 9. When we say that D is a distance, for instance, if I have point A to point B and it's 10 meters, that's a distance. Okay? If I'm at point A and if I'm at point A 10 meters but I'm looking in the direction of point B, this would be the displacement from A to B in the direction from A to B. And I hope that makes sense. We will actually come back to that and put some numbers to it to actually allow this to make more sense. Okay. Speed is simply a distance traveled over a certain time interval. And I'm going to say time interval. As an example, we can have miles per hour. That's miles per hour. A certain distance over a certain time interval. Oftentimes in this class, we will write things like this. It's a certain distance over a certain time interval. This delta, this is a Greek symbol delta, means a change in. A change in. So hopefully you've seen this before in mathematics, but if you haven't, all it means is, for instance, delta t would be a change in time. For instance, suppose I have a stopwatch, and suppose I start my clock at 12:03, and I stop my clock at 12:06. That's a time interval of 3 minutes. So this would be my starting time, and my ending time, start and end. And so delta t would be the end time minus the start time, or 3 minutes. Okay? So in general, whenever we see in this class, this is something good to know, whenever we see a delta t, let's say, it would always be the final time minus the initial time. The idea being is that we're measuring two different events. We have a start time and then an end time. Essentially, we're always going to think of this, of physics, in the sense of doing a physics experiment where we start a clock and then we stop a clock. So we have a start time and the final time. The delta time, the time interval, is always the final minus the initial. If I say, for instance, suppose I have some other variable, let's say q, and I say delta q, what I mean by this, whatever q is, it would be whatever the final q is minus whatever the initial q is. So just to give the idea that whenever you see a delta, it means a change in q. We can say a change in q, or change in whatever quantity we have right here. It's always the final minus the initial. Okay. So but now let's get back to speed and velocity. Okay. If I say I'm going to compare speed and velocity. Velocity is delta x, that's a vector, over delta t. Whereas speed is some distance over delta t. Now the difference is this. If whenever we do a physics experiment, we always set up a coordinate system. This is motion in one dimension, so we're going to have an x-axis. So we're going to assume all the motion goes up and down the x-axis. So if this is 0, this is 1 meter. Let's suppose this is in meters. 1 meter, 2 meters, 3 meters, 4 meters. Okay. Now, if I have an initial, let me write it over here. If I have an initial displacement of 1, I'm going to write that as a vector. It's basically a vector from 0 to 1 is pointing in this direction. Okay. My final displacement I'm going to say is 3. And I'm going to write the arrow over it, meaning that this is a vector quantity. It has a direction, it has a length, has a magnitude, and it points in a certain direction. Okay, so this is, I'm going to call this x1. Okay, and just to keep it offset, I'm going to say that this is x3. It has a length of 3 and is pointing in a certain direction. In this case, the direction is in the plus x direction. Same here, in the plus x direction. So displacement, the difference between different distance and displacement, displacement infers it's a distance, but it infers a direction to that distance. So it's a distance of 1, but it's pointing in the direction of plus x. Okay, and let's say that my initial time is, let's say 0. I'm going to start the clock at t equals 0, and I'm going to stop the clock at let's say 6 seconds. Okay. So when I start the clock, the initial displacement is right here. When I stop the clock, the initial displacement is right here. So here, if I, according to my formula here, I would say x final minus x initial divided by t final minus t initial. Okay, so this is 3 minus 1 going in the x direction, I'm going to say x direction, divided by 6 minus 0, and this is in meters, and this is in seconds, and this is equals 2 over 6, which is 1/3 meters per second. And it's in the direction. The direction is in the plus x direction. So my velocity in this case would be 1/3, 1/3 meters per second. So for instance, it's whatever it is. Say it's a ball. It's starting here at t equals 0, and it's rolling, it's traveling, and at t equals 6 seconds, it's right here. Okay, so the ball is moving. So now, if we compare this to speed, the speed is simply a change in distance over a change in time. The change in distance from here to here is obviously 2 meters. The change in time from here to here is 6 seconds. And again, I come up with 1/3 meters per second. numerically it's the same, but there's no sense of direction here. So you can, this gives you an idea of how you calculate velocity versus how you calculate speed. Let's just do a little bit of units conversion. Suppose this is really just for practice, but suppose we calculate a speed of, say, 10 meters per second. And we want to convert that into miles per hour. How would we do that? Again, going back to the last module, the introduction module, the way I do it and the way I would rather you do it would be using a very systematic units conversion technique. And you start like this. You go 10 meters per second. And I'm going to just do the whole thing out long. It's going to look kind of long here, but it will definitely work. Meters, 1 meter is equal to 100 centimeters. 1 meter, the meters cancel out, giving me centimeters. 2.54 centimeters equals 1 inch. That's an exact conversion. The centimeters cancel out. Now I want to go from inch to mile, so 12 inches equals 1 foot. That's an exact conversion. The inches cancel out. And 5,280 feet is equal to 1 mile. So I finally made it from meters all the way to miles. Now the seconds. Now maybe you can do this in one. There's 60 seconds in a minute and the 60 minutes in an hour. So that's 3,600 seconds in 1 hour. And the seconds cancel out. If I take my calculator here and I multiply that out, I get 10 times 100 divided by 2.54 divided by 12 divided by 5,280 times 3,600. I come out with 22 we'll call it 4 miles per hour. If this was exactly 2 significant figures, I'd round that off to 22 miles per hour. This is an example of how I would do a units conversion, and I would really want you to do something very similar to this. Okay, now I'm on page 13, going a little bit more of where we're going further. Actually, I'm going to jump over to the figure 1.3 on page 16, just because we want to go over average velocity versus instantaneous velocities, and the easiest way to talk about that is really by using a graph, very similar to the one on page 16. If you look at that, what we have, change pens here, this is time. The x-axis is time in seconds. The y-axis is position. So this would be the x position. Imagine we have the x-axis, and we're plotting this position, say 0, 5, 10, and this is in seconds, 0, 1, 2, 3, all the way up to, let's say, 10 seconds. And it looks something like this, let's say. What this means is, for instance, suppose this is a ball. If this is the actual x-axis right here, it means that as the this ball, as it travels up if it travels up in time, it travels up to a position of around 10 or so, and then it comes back down. So you see, if we start the clock here, say it travels up from 0 to 5 to 10, and then at this point it starts coming back down to here. Okay? So one question is, we can see that the speed, the speed here, actually I'm going to talk about velocity. The velocity is defined as a change in x over the change in time, and that's a vector. If I have my starting point right here at t equals 0, and I say the change in time 1, 2, 3 from t equals 0 to t equals 3, my position, my x position right here is right at 5. So if I take a straight ruler, whoops, if I take a straight ruler and I plot a line from here to here, my initial is the definition of delta is the final minus the initial minus the t of final minus t initial. My final final speed, my final position is 5. My initial position is 0. My final time is 3. My initial time is 0. And I get 5/3 meters, this is in meters, meters per second. 5/3 meters per second. Now notice, if you think of this as delta y over delta x, this is the y-axis and this is the x-axis, this is a definition of slope. It's the same thing of slope. So what we say here is that if you plot your position on the y-axis, your time on the t-axis, that the slope here, the slope of this line, actually equals the velocity. Okay? Equals the velocity. The magnitude of it, whoops, the magnitude of it is 5/3 meters per second, and it's a plus. The slope is positive, which means from a direction point of view, the positive means we're going in the plus x direction. Plus x direction. Okay. So we would say that the average velocity the average velocity from 1 to 3 seconds is 5/3 meters per second. Okay? And mathematically, it's the same thing as the slope of the line from here to here. But now notice, does the slope of this line match exactly the shape of this curve? No, it does not. The difference is the actual, did the ball move at this constant velocity from 0 to 3 seconds? No, it did not. It started a little bit slower and then it ramped up. The average velocity, notice it started at a lower velocity or lower slope during the first second and a half, but then the next second and a half, the velocity and the slope gets steeper. So really, here the velocity is slower, here the velocity is faster, but on average, the velocity from 1 to 3 is according to this straight line. So this is a definition of average velocity. A definition of average velocity would be where if we're plotting position by time, we simply connect the 2 points from the initial time to the starting point to the final time, draw a straight line, and that's our average velocity. Okay, as we make delta t small,